Good morning students. This is the first class of this course membrane technology, module 1 and lecture 1. As you know that we have divided the course into 12 modules and each module have 3 lectures. So, totally there will be 36 lectures. So, today is the first module, first lecture. Under this lecture, we will cover and learn the overview of separation processes, membrane separation basics, historical developments of membranes, what is a membrane, basically the definition of membrane and the different types of membrane. So, as you know, separation is an indispensable part of any downstream operation in most of the industries, whether it is chemical, petrochemical, biochemical, food, pharmaceutical or any other allied process industries. So, we can divide the separation processes of fluid mixtures into two categories. The first one is equilibrium separation and the second one is rate governed separation. So, let us just try to understand what is equilibrium and what is rate governed. Now, as the name indicates equilibrium separation is a process in which the product phases are in equilibrium with the feed phases. Now, what is the inherent meaning of equilibrium? Now, a system is at equilibrium if at constant pressure, temperature and composition the system is stable, not changing with respect to time. So, at equilibrium the chemical potential of the two phases are equal. So, in the rate governed separation, so the separation actually happens due to the difference in the rate of physical transport of species and that is the transport of components from a region of higher concentration to lower concentration using some medium and under the influence of a driving force. So, most of the membrane processes are actually comes under rate governed separation process. These are some of the examples of the equilibrium governed separation like distillation, absorption, adsorption, drying, and under rate governed separation process most membrane processes comes under that, whether it is osmosis, reverse osmosis, dialysis, filtration, microfiltration, etc. So, the basic principle of any separation process is that a certain amount of energy is required to accomplish the separation. Now, let us take an example. Let us see there are two substances are there A and B which will mix spontaneously. When they will mix, basically the criteria. So, when the free enthalpy of the product, that is the mixture, is smaller than the sum of the free enthalpies of the pure substances. So, the minimum amount of energy necessary to accomplish complete separation is at least equal to or larger than the free enthalpy of the mixing. So, in practice the energy requirement for separation will be many times greater than this minimum value which is denoted by W min. So, different types of separation processes exist and each require a different amount of energy. For example, let us take a simple example which is production of fresh water from sea water, the desalination actually. So, desalination of sea water can be achieved in many ways. So, or many processes. So, the first one is distillation. So, in distillation heat is supplied to the solution in such a way that the water distills, and second is freezing, the solution is cooled and pure ice is obtained. Third is reverse osmosis, which is a membrane process. So, here the solution is pressurized, allowing water molecules to pass through membrane while all the salt molecules are retained. Then electrodialysis, another membrane process. Here an electric field is applied to a salt solution between number of charged membranes and ions are forced into certain compartments, leaving water molecules in other compartments. So, and the last one is membrane distillation, though there are other methods also. In membrane distillation, heat is supplied to salt solution, causing transport of the water vapor through a non-wetted membranes. So, what we understand from this particular slide is that so desalination of seawater is a very important process and it can be achieved in many ways. The minimum amount of energy required for desalination of seawater can be obtained by a simple thermodynamic calculation. You just see this equation. So, when we take 1 mole of solvent, let us say water in this case, passes through the membrane, the minimum work done when the process is carried out reversibly can be expressed as this equation. So, W min minimum equals to pi into VW. So, where pi is the osmotic pressure of the seawater, it is approximately 225 bar, and VW is the molar volume of water, which is 0.018 liters per mole. So, we get 2.5 megajoules per meter cube. There are different separation processes which works under different mechanism. Distillation and membrane distillation, these two works in the differentiation partial vapor pressure. Similarly, freezing and or crystallization works under the mechanism of differentiation freezing tendencies, and reverse osmosis works on the mechanism of differences in solubility, diffusivity of water and salt in the membrane. Electrodialysis works under the mechanism of ion transport in charge selective ion exchange membranes. The separation processes can be broadly classified in terms of the physical or chemical properties of the components to be separated. So, the table will list out actually different physical and chemical properties, and based on which the separation processes are actually designed. So, if you look at the first one, which is size, so filtration, microfiltration, ultrafiltration, chromatography, gas permeation, all these processes are based on size. And similarly, vapor pressure, so distillation and membrane distillation comes under that, crystallization comes under freezing point, and based upon affinity, extraction, adsorption, absorption and reverse osmosis are designed based on the charge of the solute. So, ion exchange, electrodialysis, these processes works. Based on density, our centrifugation technology works, and based on chemical nature, either complexation or carrier mediated transport works. So, this table tells us that the size, the different chemical and physical properties of the solute plays an important role, and that is one of the deciding factor based on which you will decide which separation process to be adopted. So, as you know, a separation process, how do you basically select a membrane process? So, the separation must be technically feasible and the separation must be economically feasible. These two are very important things. So, let us say what is the meaning of technically feasible. So, a process must be technically feasible, that means that separation process must be capable of accomplishing a desired separation. So, whatever we want to separate, suppose let us say there is a component present in a solvent mixture and I want it to be purified to be 95%. So, I should design and develop or adapt such a technology which will give me 95% pure solute, which is my desired product. So, accomplishing the desired separation, achieve a quality product, and combination of two or more separation processes are sometimes required to meet such requirements. This combination of two or more separation processes are called hybrid technology, in which more than one unit operations are clubbed together, so that they will give us a desired quality product as well as desired efficiency. So, economically feasible means the product strongly depends on the value of the product isolated. So, if the product isolated is of low value, then it will not be economic, the process may not be economically viable. The concentration of raw material is very important. So, which means a low concentration means a higher price of pure product. The reason is that if the product which is very important for us and present in very low concentration, then we have to go for extensive downstream purification and separation part, which are very costly. So, the end product cost will increase basically. So, we can nevertheless we can reduce the cost of the product by improving the technique employed for separation. So, you can choose a particular separation process which will give me a proper efficiency as well as a pure quality of the product. So, energy cost is one of the most important costs that is associated in downstream separation, and to obtain high value products, the energy cost must constitute only very small fraction of the product. Whereas, for low value products, energy cost may be appreciably little high, it is acceptable. And other factors such as geographical location, environmental consideration, government regulation, these are also plays an important role while deciding which separation processes to be adopted. So, apart from this, what happens, sometimes political considerations also do play a role, which may not be advantageous economically, but we need to adapt it due to political considerations. So, the general objectives of separation processes are concentration, purification, fractionation and reaction mediation. Now, these are the four things based on which separation processes are designed. So, concentration means the desired component is present in low concentration in the feed solution basically, and the solvent has to be removed. And purification means there are many undesirable impurities which are present with the product, and that needs to be removed. So, we are purifying the product from other impurities basically. and fractionation means either it can be binary, tertiary, or it can be multiple fractionation. So, means there is a mixture to be separated into 2 or more desired components. Let us say one mixture is containing 2 solutes and both the solutes are important for me. So, I can choose a binary fractionation process in which the feed streams will be divided into 2 streams, basically with the help of a membrane. It is very easy to do that with the help of a membrane. So, one part will be retained and another part will go to the permeate. So, we get 2 pure products using a single membrane process. Under reaction mediation, a combination of a chemical or biochemical reaction with continuous removal of product increases the reaction rate. So, when the reaction is proceeds, basically it can be a chemical reaction or it can be a biochemical reaction, and we are withdrawing the product intermittently or continuously, then that will increase the rate of the reaction. Now, let us focus on the membrane separation process. So, as you know, most of the membrane separation processes are rate governed. So, the main crux of the separation lies in the difference of the transport of various species through the membrane. How a particular solute is getting transported through the membrane, and what is the role of the membrane in transporting that particular solute is the most important thing. So, the driving force for each such transport is generally the gradient of chemical potential. And students, let us understand what is actually the meaning of chemical potential. So, you usually write it as a mu, and you know chemical potential actually is the energy that is either it will be absorbed or it will be released by a species when number of that particular species in a particular reaction either increases or decreases. So, in other way we can say the chemical potential is the free energy that is available during the reaction that is proceeding, and since we cannot measure chemical potential directly, so we always try to express chemical potential in other readily measurable parameters, which are concentration gradient, pressure gradient, temperature gradient and electrochemical potential gradient. So, we express chemical potential basically under these 4 groups. So, presence of these one or more such gradients will result the difference in separation. Please look into this particular slide in which I am showing a schematic representation of a membrane process where the feed stream is separated into a retentate and the permeate stream. Now, students, this is the simplest form of a membrane separation device in which this is your membrane, and feed is entering from one position and retentate or the concentrate both are leaving from this, and the permeate is coming from this side. So, the membrane is being held. You can see this one, there is a module, we call it as a module. So, the module is housing the membrane. So, we need a technique to house the membrane basically. So, this is how the membrane is being housed inside a module. So, if any membrane separation process, the aim is concentration. If I am trying to concentrate something, then the retentant stream is usually with the product stream, but there is no hard and fast rule like that. We can design according to our own convenience. And if we are aiming for a purification, then depending upon the impurities, what are the molecular weight of these impurities present. So, either we can remove the impurities or retain them on the surface of the membrane, otherwise we can pass them through the permeate. Now, which component has to be retained on the surface of the membrane and which components or solutes will pass through the membrane to the permeate stream. So, there is no hard and fast rule, it has to be decided based upon certain criteria. So, criteria are, first and foremost thing is that what are the solutes and the impurities whatever it is present, their physical and chemical properties. That is what we just discussed, their size, hydrodynamic conditions and molecular weight or shape, all these things, charge also, and then accordingly we can decide a membrane cutoff. So, I can give you a very simple example. Let us say there is a mixture in which there are 2 components, and I want to remove both the components, and they are both of them are important for me. So, one solute is molecular weight is 10 kilodalton and another solute molecular weight is, let us say 50 kilodalton. So, I can either I have to choose a membrane in such a way that the molecular weight cutoff of the membrane lies in between this 10 and 50. So, eventually I can go for a membrane cutoff which is either 20, 25 or 30 or 40 depending upon the availability also. So, that the solute which is 50 kilodalton will retain on the surface of the membrane, and the solute which is 10 kilodalton and its size is much lower than the pore size of the membrane. If I choose a molecular weight cutoff of 20, 25, 30 in such a way that, so it will pass through the permeate. So, in membrane separation process, membrane is the heart of every membrane process, and it can be considered as a perm selective barrier or interface between two phases. Now, the term perm selective is also called semi permeable. Now, what is the meaning of, we need to understand this actually, what is perm selective or semi permeable. Now, the semi permeability of the membrane means that the membrane will allow certain solutes to be retained on the surface of the membrane and will allow certain other things to pass through the permeate. So, usually the solutes or ions will be retained on the surface of the membrane and it will allow the solvent to pass through. So, the driving force, as you can see, can be either concentration, it can be either temperature, it can be pressure or electromotive forces. So, any one of these or a combination of multiple of these also will result in the separation of the components. So, phase 1 is usually considered the feed, that is we also call as upstream side phase, and phase 2 is considered the permeate or downstream side. In any membrane separation process, separation is achieved because the membrane has the ability to transport one component from the feed mixture more readily than any other component in the feed solution. So, performance of the membrane is given by the two parameters. First one is selectivity, okay, and the second one is flow through the membrane. The term flow through is actually called as flux or the permeation rate. So, flux is most important in membrane studies. So, we will discuss in the next slide what is flux actually. So, it can be denoted as the volume flowing through the membrane per unit time and per unit area. So, what is the amount of volume that is passing through the membrane per unit area and per unit time is called as flux. So, please see the conversion table for volume fluxes. So, you can use this table to convert fluxes into volume fluxes and into different other fluxes, and the volume flux may easily be converted into mass flux or mole flux by using the density and molecular weight. You can see the equation. So, the volume flux is converted into mass flux by multiplying with density and converted to mole flux by multiplying with density and dividing by the molecular weight. So, capital M is the molecular weight. So, in case of transport of gases and vapors, same units may be applied, but with different meaning. The reason is that the gases behave differently from liquids. The volume of gas is strongly dependent on pressure and temperature, while liquids are not. So, in order to compare gas fluxes with each other, the volume is always given under standard conditions, which is at 0 degree centigrade and 1 atmospheric pressure. So, in case of 1 mole of ideal gas, the volume is V by N equals to RT by P is 22.4 liters. So, now let us discuss what is selectivity of the process. So, selectivity of a membrane towards a mixture is generally expressed by two parameters. One is called retention, another is a separation factor. You will be hearing this term retention many times in our discussions in our subsequent lectures. So, retention is given by this equation R equals to Cf minus Cp by Cf, which is 1 minus Cp by Cf. So, here Cf is the solute concentration in the feed side and Cp is the concentration of the solute in the permeate side. Since R is a dimensionless parameter, it does not depend on the units in which the concentration is expressed. The value of R actually varies from 100% to 0%. So, if it is 100%, that means it is complete retention of the solute, everything is getting retained on the surface of the membrane, and if it is 0%, that means the solute or solvent pass through the membrane freely and nothing is getting retained. So, membrane selectivity towards gas mixtures and mixtures of organic liquids is usually expressed in terms of separation factor alpha. So, many of you who have studied distillation, they may be knowing alpha, which is relative volatility in distillation. So, here we define alpha for a mixture of components A and B as alpha A by B equals to Ya by Yb divided by Xa by Xb. The Ya and Yb are the component are the concentration of component A and B in permeate, while Xa and Xb are the concentration of component A and B in feed. So, basically it is the mole fraction of the component A and B in permeate to that of the mole fraction of the component A and B in feed. So, selectivity alpha is chosen in such a way that the value is usually greater than unity. So, if the permeation rate of component A is larger than that of component B, the separation factor is denoted as alpha A slash by B. So, similarly, if the component B is permeates preferentially than component A, then we can write it as alpha B by A. So, if alpha A by B equals to alpha B by A equals to 1, that means no separation is achieved. So, if the separation has to be achieved, the separation factor alpha should be always more than 1. So, the SI unit for amount of substance is usually mole, but kilogram is also used frequently as you know. The concentration term is usually expressed either as mass concentration, that is denoted by Ci, or molar concentration denoted by Ni. So, many books use different notations, but you should not confuse with this. You must understand the inherent meaning of the terms actually, and the composition of a solution or mixture can be described by means of mole fractions, weight fractions, or volume fractions. So, these are the concentration units. For mass concentration it is kilograms per meter cube, for mole concentration it is moles per meter cube, for mole fraction, that is mole by mole, it is dimensionless, weight fraction W by W it is dimensionless, and volume fraction V by V it is again dimensionless. So, let us understand what are the benefits of membrane technology. So, one of the most important benefit of the membrane technology is the energy consumption is really low. So, since membrane is the heart of the process and it does not require any energy to run the membrane process, apart from the energy that is only required to supply the feed or pump the feed from the feed tank to the membrane module. And sometimes you need to supply some this one buffer solution, for that also it needs to be pumped. So, the pumping cost actually comes into picture, and membrane processes can be easily combined with other separation process. That is another beauty of this membrane process, that it can be hybridized very nicely with another process. One of the classic example of membrane hybridization is with distillation. So, this we will discuss in one of our classes when we will discuss actually pervaporation later on. And upscaling is easy for membrane process. So, since membrane this one scale up is mostly it is linear, which is also not a very good thing actually when we go for upscaling. Why it is? Because the scale up factor is linear, so it directly depends upon the membrane area. Let us say if I am processing 1 liter of a mixture using a 10 centimeter square membrane, then I can scale it up usually to 100 liters by multiplying a factor of 100 into 10 centimeter square. So, into 10 centimeter square into 100, okay. So, it will be 1000 centimeter square of the membrane. Now, since the scale up is so linear, the problem is that I cannot usually make a membrane module in such a way that I can have a 100 meter square or 1000 meter square of the membrane sheet and housed in a module. So, that is not possible technically. So, that is a little problematic, though for a design purposes upscaling is easy. However, since the factor is linear, so that is not so advantageous. So, membrane properties are variable and can be adjusted. So, I can always prepare a membrane which will suit to my requirement. So, for example, let us say I am trying to separate certain ions, certain solutes which are charges. So, I can design a either a cation exchange membrane or a anion exchange membrane in such a way by imparting certain functional groups which are having fixed either cationic charges or anionic charges, okay, during the preparation of the membrane, so that this particular separation can be achievable. So, the inherent meaning of this is that I can always play with the membrane material properties and always can make a membrane tailor made. So, and another beauty of the membrane processes is that no additives are required. So, I can give you an example of such a process. Let us say there are two, there is a azeotrope of closed boiling point mixtures, which is usually separated using a azeotropic distillation. in which we added a third component to separate it. In case of membrane, if we can separate it using a membrane process where no additives will be required. So, this saves the extra cost actually. But all is not so well for the membrane processes. There are certain drawbacks and disadvantages also. The major problem is concentration and fouling. So, let us try to understand what is concentration. Let us see, this is the membrane in which our separation is happening, the feed is coming in such a way. So, the solutes are getting deposited on the surface of the membrane. So, initially there will be the monolayer deposition. So, when the process proceeds, so we will have another bilayer deposition. So, this build up of actually deposition is actually called as concentration polarization. So, which is the deposition of the solutes on the surface of the membrane. Now, as the membrane process is continuous, this will increase, more and more solutes will get deposited on the surface. Now, let us understand what is the meaning of fouling. So, in membrane, fouling can be of two types. One is external fouling and another is internal fouling. So, since membranes are porous in nature, let us say this is one of the pore, and external fouling can happen if the solute is getting deposited on the surface of the membrane like this. So, it is blocking the basically the pore of the membrane. So, this is what is called external fouling. And let us say another pore in which pores can be of different types and sizes. Okay. So, another pore, let us say very small solute, okay, it passes through the membrane and it gets deposited on this particular area which is a constricted passage inside the pores. So, this can be internal fouling, or it can come here and get deposited here and but not moving out here. So, this means the membrane, the particular pore of this particular membrane is getting fouled, and this is called internal fouling. So, either external or internal fouling, both are not good for the membrane processes, but however, we can always clean the membrane from the back side by using back flushing. So, I can always use water or other chemicals to flush it from the back side, so that all these depositions will go away. So, this is possible, but in a long term process perspective, when I am using the membrane continuously for a infinite period of time, then these are the things which we need to take care of. So, another important thing is the membrane lifetime. So, usually the lifetime of membrane is less than to other separation processes, and the low selectivity of the flux. So, flux will be usually, if you look at, so initially when the process, let us say this is time and this is flux. So, when the membrane process will start, so your flux will be higher, then slowly it will gradually decrease and it will become constant. Okay. So, this process is called flux decline profile. We will discuss in detail in one of our classes about this, but just trying to understand that the membrane separation process initially the flux will be higher, then gradually it decreases, and it decreases due to this concentration polarization and fouling. So, and upscaling factor is more or less linear. This is what I just describe you, why the upscaling is easy and why the upscaling is not so good because of linearity. So, let us move ahead. Though I told you that membrane fouling and concentration polarization should not be considered as a disadvantages, okay, because this phenomena is anyway inherent in any separation process. However, what is required is that we needs to take certain measures such that this phenomena has to be reduced. We cannot do away with it exclusively. So, what will be the target is, our target is that how to reduce concentration polarization and fouling. Because you do anything, you take any measure, there will be certain concentration polarization or deposition of the solutes on the surface of the membrane, as well as certain solutes will block the pore of the membrane, as well as they will get inside the membrane pores and thereby blocking the pore for further use. So, a membrane technology is widely used in various industrial areas such as food and beverages, metallurgy, paper, pulp, textiles, pharmaceuticals, dairy, biotechnology industries, chemical industries, and water treatment for both domestic and industrial supply. Whenever we say water, this water usually takes into account both the potable water treatment as well as the wastewater treatment. So, let us now discuss the historical development of membranes. Actually, membrane is nothing new. If you look at this particular size, you can understand that in 1748, Nollet is the first person who has discovered the phenomenon of osmosis. Okay, so by permeation of water through a diaphragm, it long back. So in 1907, Becquerel devised a technique to prepare a nitrocellulose membrane of graded pore size, which was determined using a bubble test, and by the early 1930s, microporous colloidal, which is nitrocellulose membranes, were commercially available. So, during the next 20 years, by 1950, the early the microfiltration technology was expanded to other polymers, notably cellulose acetate. The golden age of membrane technology actually began in 1960 with the invention of Loeb and Sourirajan, the first asymmetric integrally skinned cellulose acetate RO membrane, reverse osmosis membrane. So, this is one of the most important breakthrough in membrane science and technology. So, this particular development by Loeb and Sourirajan, these are the two scientists who has manufactured or designed this first asymmetric skin membrane. So, this actually stimulated both commercial and academic interest, and the first in desalination by reverse osmosis, and then in other membrane applications and processes. So, after that actually so many researchers or scientists have taken keen interest in the development of membranes, and so many notable things actually developed. So, methods of packing of membrane in large membrane areas such as spiral wood, hollow fiber, capillary and platen frame modules were also developed, and advances were made in improving the membrane stability. Stability is also a very important issue. And by the year 1980, microfiltration, ultrafiltration, reverse osmosis and electrodialysis were all established processes with large plants installed worldwide. Everywhere you will see now these are all commercial technologies. So, this slide will just let you know in a tabular format how the development of membrane has taken place. Nollet in 1748 has coined the term osmosis, then Fick in 1865 proposed the first synthetic membrane from nitrocellulose, then in 1887 Van 't Hoff developed the theory of osmotic phenomenon. That is the theoretical development basically, and in 1962 Loeb and Sourirajan has discovered the first asymmetric skin membrane. In 1975 Potter has given the classification of the membrane pressure based membrane processes, and in 1977 Goddard has developed the model for facilitated transport. This is another milestone in membrane technology with the invent of facilitated transport, and in 1980s the emergence of industrial gas separation membranes processes has come into picture. So, with the development of Monsanto a membrane for hydrogen separation, Dow's nitrogen separation membrane from air, Cyanara and Separex membranes for separating carbon dioxide from methane, usually from the biogas. Then in 1986 Yoshikawa has developed the membrane with active centers, and in 1990 Rattenbeck has developed the first hybrid membrane processes. Now, these are the hybrid processes are also commercialized and are in operation in many industries including the refineries. So, if you look at country wise, so microfiltration, ultrafiltration, these are developed in 1920s and 30s in Germany. However, they are all small scale, and later on in 1950-55 hemodialysis and electrodialysis membranes were developed in Netherlands and United States. The artificial kidney which was actually developed in Netherlands in 1950 was a small scale one. Now, we have industrial scale production of these things, and the first desalination plant that was designed in United States in 1955 is a industrial scale electrodialysis plant. Then later on in United States ultrafiltration and gas separation was developed in 1960s, 79, 80s. So, for hydrogen recovery and as well as concentration of macromolecules. Then membrane distillation was invented in 1981 and commercialized in Germany for the concentration of aqueous solutions, but that was in small scale. Now, it is available in large scale, and in pervaporation another beautiful membrane technology that was developed in Germany and Netherlands in 1982 for the dehydration of organic solvents in industrial scale. Now, understand what is the definition of a membrane. So, long back, editor-in-chief of the Journal of Membrane Science has actually thrown into public that please suggest what can be the definition of a membrane. So, leading membrane scientists across the world has proposed so many different types of definition of the membrane according to their wisdom, and few of them are listed by the editor-in-chief and published in the Journal of Membrane Science. So, you can refer to it later on. So, the word membrane actually originated from a Latin word which is called membrane, which means essentially skin. So, the membrane can be defined as a selective barrier which separates two phases and restrict the transport of various compounds in a selective manner. So, the term selective is being inherent to a membrane or membrane process. So, this is a macroscopic definition. Please note that it says nothing about the membrane or membrane process. So, a membrane can be thick or thin, its structure can be homogeneous or heterogeneous, and transport can be active or passive. So, passive transport can be driven by pressure, concentration or temperature disturbance, basically by the virtue of a gradient. And membrane can be natural, basically biological, or it can be synthetic, it can be neutral also, it can be charged also. So, a membrane can be defined as a structure having lateral dimensions much greater than its thickness, through which mass transfer may occur under a variety of driving forces. So, a membrane can be a selective barrier or it can be a contacting barrier. If it is a selective barrier, then the membrane controls the exchange between two regions adjacent to its surface in a very controlled manner. And if it is only a contacting barrier, then the main function of the membrane is to contact the two phases between which the transport will occur. And a membrane is nothing more than a discrete thin interface that moderates the permeation of chemical species in contact with it. Now, this interface phase may be molecularly homogeneous. So, that means it is completely uniform in composition and structure, or it may be chemically or physically heterogeneous, which essentially means that containing so many pores of finite dimensions and consisting some form of layer structures. So, let us see what are the different types of membrane processes, what are the driving forces and separation size range. The basic membrane processes are starts with microfiltration, ultrafiltration, then reverse osmosis, electrodialysis, dialysis and nanofiltration. So, nanofiltration and reverse osmosis actually overlap each other in terms of driving force as well as separation size range. So, microfiltration, ultrafiltration, reverse osmosis and nanofiltration all are operated under the gradient of pressure. So, these are all pressure driven membrane processes, and the separation size range, as you can see that when we proceed from microfiltration to ultrafiltration, RO and electrodialysis, dialysis, the size of the solutes that will be separated is usually decreasing. So, which essentially means that when I am trying to separate a smaller size solute or particles, then I need to have more pressure. So, the pressure increases when we go from microfiltration to nanofiltration. So, every membrane separation process is characterized by the use of a membrane to accomplish a particular separation, and the membrane has the ability to transport one component more readily than others because of differences in either physical or chemical properties or the combination of two between the membrane and the permeating components, which essentially means that when the membrane separation is happening, so the physico-chemical properties of the solutes that we want to separate as well as the physical and chemical properties of the membranes that is separating are both are essential to achieve a particular separation. So, transport through the membrane takes place as a result of driving force acting on the components in the feed. Permeation rate through the membrane is directly proportional to the driving force. So, the flux force relationship can be described using a phenomenological equation which is given by this equation J is the flux equals to minus A dx by dx. So, here A is phenomenological coefficient and dx by dx is the driving force expressed as the gradient of x. Now, x can be either temperature, it can be concentration, it can be pressure, or it can be electromotive force also. So, along a coordinate x perpendicular to the transport barrier. So, for a pure component permeating through the membrane, it is possible to employ linear relationships to describe transport. However, when two or more components permeate simultaneously, such relations cannot be generally employed since coupling phenomena may occur in the fluctuation forces. We will discuss what is this coupling phenomena later on in one of our classes when we discuss non-linear thermodynamics. So, this coupling phenomena can be described in terms of the formalism of non-equilibrium thermodynamics. The transport through the membrane can be classified as active, passive or carrier mediated transport. The term active transport can be applied to flows that are directed against the conjugate driving forces, and passive transport are those where flows are directed in the direction of the conjugate driving forces. And in facilitated or carrier mediated transport, there is a carrier molecule which is a extra thing which resides in the membrane. Okay. And it is accomplished by means of the following steps. So, association with a carrier molecule at the interior surface. So, that means the solute which we want to separate is first getting associate itself with the carrier molecule in the interior surface of the membrane, then transport of this permeate and carrier complex across the surface of the membrane, and then dissociation of the permeate molecule at the interface surface. Let us see how this will happen. Let us say this is a membrane, okay, and this is a carrier molecule which is present inside the membrane, and this is a solute. Now, this solute when it comes into contact with the membrane, okay, come to this interface, okay, then it will try to associate with this carrier. Now, then they will form they will try to associate and they will form a intermediate complex. So, this is a intermediate complex, permeate carrier complex. Now, this should transport across the membrane. Then what it comes to the permeate side of the membrane here in this interface, then it will dissociate itself. So, the solute will come here and the carrier will again go back to the membrane and it will remain inside the membrane. So, these are some of the phenomenological equations of different fluxes. So, mass flux, volume flux, heat flux, momentum flux and electrical flux. So, in mass flux which is fixed flux actually, the D is the diffusivity which is the phenomenological equation. In Darcy's law it is LP permeability, in Fourier's law it is lambda, and in Newton's law it is the kinematic viscosity, and in Ohm's law it is the resistance. So, these equations are very important. This will be using for various processes later in our classes. And in membrane processes, the driving force can be gradient in pressure, concentration, electric potential or temperature. This we have discussed earlier also. So, other than the driving force, the membrane itself plays a major role determining the selectivity and flux. This is very important. And this is the inherent meaning of this, the physical and chemical properties of the membrane also determines the separation. So, the nature of the membrane determines the type of application, ranging from the separation of microscopic particles to the separation of molecules of an identical shape and or size. Let us look at this particular diagram. So, this tells us that what are the possible applications of the membrane. So, we can have a liquid-liquid separation, we can have a liquid and gas separation, we can have a gas and gas separation. The first one is usual microfiltration, ultrafiltration, reverse osmosis and these things, and liquid gas separation is usually pervaporation, and gas separation is it can be any gaseous separation like this separation of nitrogen from air, separation of carbon dioxide from biogas, etc. So, these are some of the membrane processes and their driving forces. So, phase 1, phase 2 and driving forces. So, under microfiltration we can go for a liquid-liquid separation. The driving force is of course pressure. You can see that for microfiltration, ultrafiltration, nanofiltration, reverse osmosis, all these things and vapor permeation, the driving force is our delta P. And for gas separation also the driving force is delta P. For pervaporation it is separating a liquid and gas phase, the driving force is again delta P. In case of electrodialysis the driving force is delta E and the electromotive force, and in case of dialysis gradient or concentration difference. Okay. Diffusion dialysis is also again concentration difference, and in case of thermoosmosis or membrane distillation which are actually thermally driven membrane processes. So, both thermal gradient, temperature gradient as well as pressure gradient is important. So, let us now understand the different pressure range and the flux ranges of the important membrane processes. So, I have given 4 processes here: microfiltration, ultrafiltration, nanofiltration and reverse osmosis. So, you can see then as we proceed from microfiltration to ultrafiltration, then nanofiltration and reverse osmosis, the pressure that is required is increasing. That is because of the fact that as we proceed from microfiltration to ultra, nano and reverse osmosis in that sequence, then the flux is actually decreasing as we need more pressure, and the solutes that is getting separated is also getting becoming smaller in size. So, let us now discuss the types of membranes. So, the membrane process classification we will discuss in detail in the next class. So, in this course our discussion will be mainly limited to the synthetic membranes, excluding all biological membranes. So, we are not discussing any biological system here. So, a normal filter also meets the definition of a membrane. The usual filter, cloth filter or any such filter that is available at home or labs. However, by convention the filter is usually limited to structures that separate particulates of suspensions larger than 1 to 10 micron. So, the definition lies actually the difference between the conventional filter and membrane is the sizes that is getting separated. So, the principal types of membranes are listed below. So, we can have isotropic membrane, anisotropic membranes, we have ceramic or inorganic membranes, and we can have liquid membrane. So, liquid membrane is a latest technology. In one class we will discuss in detail about liquid membrane later on. So, all membranes can be classified into symmetric and asymmetric membranes also. So, isotropic membranes are symmetric membranes, anisotropics are asymmetric membranes. So, under isotropic we can have microporous membrane, non-porous dense membranes and electrically charged membranes. So, let us see one by one what are those things. So, what are basically isotropic membranes? So, isotropic membranes have a uniform composition structure throughout and then can be either porous or dense, that means non-porous. The resistance to mass transfer in these membranes are determined by the total membrane thickness. So, thickness of the membrane plays the most important role. So, that is the resistance, the membrane thickness provides the utmost resistance to the separation or the mass transfer basically. So, a decrease in membrane thickness results in an increased permeation rate. Let us see what are the microporous membranes. So, these are similar to conventional filter, however, with very small pore sizes. You can see in this picture how the isotropic microporous membrane looks like. All particles larger than the largest pores are completely rejected by the membrane. That means, the solutes whose sizes are more than the size of the pore will all be retained on the surface of the membrane, and particles smallest than the largest pore but larger than the smallest pore are partially rejected according to the pore size distribution. Now, please understand that membranes do not have uniform pores, they have a pore size distribution. So, I can just try to draw one thing. You can see the pore size distribution, it something looks like that. So, we can have a narrow pore size distribution like this also, or we can have a wide pore size distribution like this also. So, which essentially means that membrane do not possess uniform pores except maybe some zeolite membranes. Most of the membranes which are commercially available has a pore size distribution. So, particles which are smaller than the smallest pores will of course pass through the membrane, and separation of solute is mainly a function of molecular size of the solute and pore size distribution of the membrane. Microfiltration and ultrafiltration membranes falls under this category. Then let us understand what is a non-porous dense membrane. So, this type of membrane consists of a dense film through which permeates are transported by diffusion under the driving force of a pressure, concentration or electrical potential gradient. So, there is no pores in this type of membranes, that is why these are non-porous membranes, and the separation of various components of mixture is related directly to their relative transport rates within the membrane. So, how they are getting transported, the diffusion rates and all these things of the solute plays an important role, which are determined by the diffusivity and solubility in the membrane material. Two things are very important. First is the diffusivity and solubility. So, the solutes which are supposed to be transported must be soluble in the membrane, and they should have a proper diffusion rate, so that they will be transported across the membrane. Thus, this type of membranes can separate permeates of similar size if their concentration in the membrane material differ significantly. So, dense membranes has the disadvantage of low fluxes unless they can be made extremely thin. For this reason, dense membrane properties are incorporated into the top skin layers of the asymmetric membrane. So, usually what happens, we can prepare a skin membranes like this. Okay. So, we can have a very small thin layer which is dense membrane, and we can have a porous sublayer here usually of microfiltration rays. So, this is porous. Okay. So, this provides the support, and this is the skin layer, okay, which is non-porous. Please understand that this skin layer is actually will do the separation, and this particular porous layer is providing a mechanical support to hold this skin layer. So, most of the gas separation, per-evaporation, reverse osmosis processes uses dense membrane to perform the separation. So, next is the electrically charged membranes. So, the electrically charged membranes can be dense or it can be microporous, both it can be both also, but most are commonly very finely microporous. Most of the electrically charged membranes are microporous with the walls carrying fixed positive or negatively charged ions. So, you can see here, so these are containing some negatively charged ions. So, you can have positively charged ions also imparted inside the membranes. So, a membrane with fixed positively charged ions are referred as anion exchange membranes, because it will bind the anions in the surrounding fluid, and a membrane containing fixed negatively charged ions are called cation exchange membranes, because it will exchange cations. And the separation with charged membranes is achieved mainly by the exclusion of the ions of the same charge as the fixed ions of the membrane structure, and to a much lesser extent by the pore sizes. So, pore sizes actually is not playing a major role here. The major role is ion exchange, and separation is affected by the charge and concentration of the ions. So, concentration of the ions also very important while deciding the separation. So, let us understand what are anisotropic membranes. So, these membranes consist of a number of layers, each with different structures and permeabilities. So, a typical anisotropic membrane has a relatively dense, extremely thin surface layer, which is skin. I just draw in the previous slide. So, to make you understand the skin layer, which is also called as a perm selective layer, supported on an open much thicker porous substructure. So, the separation properties and permeation rates are determined exclusively by the surface layer. So, the surface layer or the skin layer is doing the separation. The below layer, which is mostly porous, then the surface layer is providing the mechanical support, and virtually it has nothing to do with the separation. The resistance to mass transfer is determined largely and completely by the thin surface layer, the skin layer. So, the advantages of higher fluxes provided anisotropic membranes are so great, that means the flux are very high, that almost all commercial processes nowadays are using this type of membranes. So, the first membrane here you can see, this is the Loeb and Soorirajan anisotropic membrane, okay. And the next one is the thin film composite membrane, in which there is a separate thin film fabric prepared and then fused with this porous layer. The next membranes are inorganic membranes, are also called ceramic membranes. So, they are very versatile and can be operated at elevated temperature. That is the beauty of these ceramic membranes, that they can withstand higher temperature, almost close to 1000 degrees centigrade, and they can withstand higher pH, their high chlorine resistance, their mechanical stability and chemical and thermal stability is very good. So, ceramic membranes normally have an asymmetric structure composed of at least 2 or 3 different porosity levels. So, inorganic membranes offer potential application such as air separation by mixed oxygen ionic and electronic conducting ceramic membranes and molecular sieve carbon membrane, then hydrogen separation by metal, silica, zeolite and proton conducting ceramic membrane, hydrogen separation by zeolite and silica membranes, carbon dioxide separation by silica and zeolite membrane. So, these are all commercialized processes. You can see these are actually tubular ceramic membranes, this figure shows. Then the next membrane type of membrane is liquid membrane. So, liquid membrane is a latest addition to the membrane group. So, it is significantly its application is increasing after the facilitated transport came into picture. So, it utilizes carriers to selectively transfer components such as metal ions at a relatively high rate across the membrane interface. So, what is a liquid membrane? So, liquid membrane literally is a membrane which is made up of a liquid. So, it consists of a liquid phase, that is a thin oil film existing either in supported or unsupported form, that serves as a membrane barrier between two phases of aqueous solutions or gas mixtures. So, liquid membranes are used on a pilot plant scale for selective removal of heavy metal ions and organic solvents from industrial waste streams. They have also been used for separation of oxygen and nitrogen. What you are seeing here students in this picture is that supported liquid membrane, where you can see this is one particular pore. Now, this pore is filled with organic liquid, which is membrane phase. So, this is organic liquid which is the membrane pad, and this is the support. So, we can it is very easy to prepare a liquid membrane. You know, if you have a U-tube manometer type of thing in the glass, so you can have something like this. So, you can in one limb you can pour your liquid membrane, okay, from here, let us say you pour from here, okay, and it comes and deposited here. So, it will be here. So, from here you can pass your feed, okay. So, and here the feed contents here, okay, and here we can have a extract phase, and this is feed phase, and this is the membrane. So, the component that we want to transport will eventually come through the membrane phase, then it will go to the extract phase. This extract phase will help in holding the solutes, and will thereby limiting the back diffusion of the solute from the extract phase to the feed phase. So, this is the simplest form of liquid membrane that we can have. So, students, today we understand what is a membrane and what are the types of membrane, as well as we understand what is flux, and we understand what is the different separation processes also. In our next lecture, under the same module, we will discuss the different types of membrane processes and their classification, and what are the various advantages and disadvantages of different membrane processes, and what are their major applications. So, thank you very much. If you need any clarification, you can always write to me at this email ID kmohanty@iitg.ac.in. Thank you very much.